Imagine a car taking a curve at constant speed. The speedometer may stay at the same number, but your body still feels pushed sideways. That tells us something important. Even when speed is constant, the motion is still changing because the direction of velocity is changing. In this video, we will focus on centripetal acceleration and centripetal force. The word centripetal means center seeking, so both the acceleration and the net force point toward the center of the circular path. This is the key idea for the whole lesson. In uniform circular motion, the object does not speed up or slow down, but it is constantly turning. To make an object turn, its velocity direction must change, and that change requires an acceleration toward the center. We will first explain why the acceleration point inward, then use the equations for centripetal acceleration and centripetal force. Finally, we will solve two examples: an ultracentrifuge spinning at very high angular speed and a car moving around a curve. Let us begin by looking at why circular motion has acceleration even when speed is constant. In uniform circular motion, the speed is constant, but the direction of the velocity vector is not constant. This statement is the foundation of centripetal acceleration. Velocity is a vector, so it includes both magnitude and direction. If the speed stays the same but the direction changes, then the velocity changes. On the diagram, the object is moving along a curved path. At one point, the velocity vector is tangent to the circle. A short time later, the object is at a different point and the velocity vector is tangent in a new direction. The small inset shows the change in velocity, delta v. When we compare the two velocity vectors, the change in velocity points toward the inside of the curve. Since acceleration is the change in velocity divided by the change in time, the acceleration also points toward the center of curvature. This can feel surprising because students often connect acceleration only with speeding up, but acceleration means any change in velocity. Change in direction is also acceleration. Now we can write the equation for the size of this inward acceleration. The centripetal acceleration points toward the center of the circle. It is in the same direction as the change in velocity delta v. The magnitude of centripetal acceleration can be written in two equivalent ways. A sub c equals v squared divided by r, or A sub c equals omega squared times r. Use A sub c equals v squared over r when the problem gives the linear speed v and the radius r. Use A sub c equals omega squared r when the problem gives angular velocity omega and radius r. Let us interpret the first form. If the speed increases, centripetal acceleration increases a lot because speed is squared. When radius becomes smaller, the acceleration also becomes larger. If the radius becomes smaller, the acceleration also becomes larger. That is why a sharp curve at high speed can be dangerous. The unit is meters per second squared, just like any acceleration. The direction is just as important as the magnitude. The acceleration is not in the direction of motion. The velocity is tangent to the circle, but the centripetal acceleration points inward toward the center. Once there is an inward acceleration, Newton's second law tells us there must be an inward net force. Centripetal force is the net force required to keep an object moving on a circular path. This wording is important. Centripetal force is not usually an extra new force. It is the name we give to the net inward force that produces circular motion. For example, for a car turning on a flat road, static friction can provide the centripetal force. For a ball on a string, tension can provide the centripetal force. For a satellite orbiting Earth, gravity provides the centripetal force. The direction of the centripetal force always points toward the center of the circle. As the object moves, the inward direction changes because the center is in a different direction relative to the object at each point. Using Newton's second law, F net equals ma, the inward net force is mass times centripetal acceleration, so we can write F sub c equals ma sub c, and that is equals to m times v square over r, and that is also equals to m times omega square times r. A common mistake is to draw a separate arrow labeled centripetal force in addition to the real force. Instead, identify the real force or combination of real forces that points inward and set that net inward force equal to m times v squared over r. Now let us practice using the angular velocity form of centripetal acceleration in an ultracentrifuge example. In this example, we calculate the centripetal acceleration of a point 7.5 centimeters from the axis of an ultracentrifuge spinning at 7.5 times 10 to the power 4th revolutions per minute. Then we compare that acceleration to the acceleration due to gravity. First, we have to identify what is given. The radius is 7.5 centimeters, which must be converted to meters. So the radius r is equals to 0.0750 meters. The angular speed omega is given by 7.5 times 10 to the power 4 revolutions per minute. So we have to convert this into radians per seconds. So let's do that. So omega is equals to 7.5 times 10 to the power 4 revolutions per minute, and multiplied. So we have 2 pi radians per 1 revolution multiplied with 1 minute is 60 seconds. And then this is equal to 7.50 times that 4. And then here you can see this revolution cancels out, and then this minute cancels out. So we get 7.5 times 10 to the power 4 times 2 pi radians divided by 60 seconds. So this is equals to 7,854 radians per second. And then we can use the equation A sub c equals omega square r to calculate the centripetal acceleration. We can substitute the values. So 7,854 radians per second squared times 0.0750 meters, and this is equals to 4.63 times 10 to the power 6 meters per second square. This is an enormous acceleration. To compare it with gravity, we can divide this by g, which is 9.8 meters per second squared, and then we get the ratio between centripetal acceleration and g is equals to 4.63 times 10 to the power 6 meters per second squared divided by 9.8 meters per second squared. And this is approximately equals to 4.72 times 10 to the power 5. So the centripetal acceleration is approximately 4.63 times 10 to the power 6 meters per second squared, which is about 4.7 times 10 to the power 5 times the acceleration due to gravity. That large ratio is exactly why centrifuges are useful. They can create extremely large inward acceleration by spinning objects at high angular speed. Next, we will use the force form of the same idea for a car moving around a curve. Now consider a 900 kilogram car moving around a curve of radius 500 meters at a speed of 25 meters per second. Part A asks for the centripetal force exerted on the car. Since we are given mass, speed, and radius, we can use the equation F sub c equals m times v square over r to calculate the centripetal force. Part B asks for the minimum coefficient of static friction between the tires and the road, assuming the curve is unbanked. This is very important physical point. On a flat, unbanked curve, the force that keeps the car moving in a circle is static friction. The car tends to continue straight, but friction between the tires and the road provides the inward net force needed to turn the car. The free body diagram shows weight downward, normal force upward, and friction horizontally toward the center of the curve. Since there is no vertical acceleration, the normal force equals mg. Horizontally, static friction provides the centripetal force. So for part B, the minimum friction condition is given by F sub s is equals to mu sub s times n. And this frictional force provided must be at least equals to the centripetal force needed to keep the car moving in the circular path. Now let us calculate the centripetal force and then solve for the minimum coefficient of static friction. So first let's write down the given values. M is 900 kilograms. Radius of the curve is 500 meters. The speed is 25 meters per second. For part A, we can use the equation Fc equals mac, which is m times v square over r. So here we can substitute the values. So 900 kilograms times 25.0 meters per second, and this is squared divided by 500 meters, and this is equals to 1125 newtons. For part B, we need to find the coefficient of static friction. So we can use the equation Fc is equals mv square over r equals mu sub s times n, and this is also equals mu sub s times mg. So from here we can get mu sub s is equals to v square over rg, and we can substitute these values. So 25 meters per second square divided by 500 meters times 9.8 meters per second square, and this is equals to 0.13. The minimum coefficient of static friction is 0.13. If the available static friction is less than this, the tires cannot provide enough inward force and the car will skid outward from the curb.